All right, hey guys, welcome to Thursday's class. I need you to start by adding number 88 to your table of contents, relative dating, number 88. And after you're done, be prepared to write some notes and then do some activities. The sub can pause the video if you need her to catch up with something that you missed. If the me talking and the notes seem out of sync, just wait a few seconds, it'll catch up. All right, guys, this is going to be number 88 in your table of contents. It's called relative dating, which, by the way, is not the same thing as going to the prom with your cousin, okay? That's not what we're talking about when we say relative dating. When we talk about relative dating, we're talking about figuring out the age of some fossils or just the rocks by looking at nearby rocks or fossils. That's what makes it relative, okay? Relative. Now, later on, we're going to talk about absolute dating, which is where you find out using radioactivity. But for now, they're just going to compare. And the way we compare is by using index fossils. I'm going to talk about what index fossils are in just a minute. Now, all of this is based on a simple idea, which is called the Law of Superposition. Sounds like a pretty neat thing, right? The Law of Superposition. But all that really means, super means above, and position is position. So the Law of Superposition basically says one thing, okay? It says that deeper fossils or rocks are older. And that's because they got laid down first, and the newer ones got built up on top of that, okay? One really important thing about relative dating that you have to understand, relative dating is approximate. It does not give an exact date. Okay? It does not give an exact date. Now, relative dating relies on index fossils, as we mentioned earlier. Index fossils. Index fossils are the fossils of animals that have three qualities that are really useful to us. For one, they are widespread in locations. So for something to be an index fossil, it must have been living in a lot of different places on Earth, so that when we find it, it's not a super rare thing. Second, it has to have lived during a specific time. So generally, we like index fossils to be creatures that only live for a short period of time, so that when we find them in the rocks, we know exactly how old those rocks are, or pretty close to exactly. And they have to be well preserved, okay? They have to be things that leave behind good fossils. Remember, we talked about earlier this week that some organisms don't leave behind good fossils, others do, and so it's important that you understand that index fossils have to leave behind good, well-preserved fossils. So basically, the way that relative dating works is that you've got these layers in the ground, okay? If you find a mystery fossil right here, and below it is an index fossil A, and above it is an index fossil B, we might know that the age of index fossil A, because we know it so well, it has to be one that we know really well, that maybe this one is 67 million years old, and we know that index fossil B is maybe 40 million years old. That tells us that the mysterious new fossil must be somewhere between 40 and 67 million years old. Okay? That's how relative dating works. Now, you're going to practice this doing a couple of activities, which will be explained in the next section. But in the meantime, make sure you get these notes complete. All right, now it's time for each team, each set of tables, to get their own brown envelope. You can pause here and wait until everybody has their envelope, because you'll need it before we move on. All right, guys, today in class you're going to do two activities that involve this envelope that you'll be given to your team. So the first thing you have to do is open up the envelope and empty out all of the cards that are inside, okay? Now, there's going to be two different kinds of activities. One involves the bigger cards and one involves the smaller cards. So I'd like you to take the bigger ones off to one side, and the smaller sheets, you're going to take those off to one side. Now the bigger ones we don't need right away. That's going to be for activity 2. So go ahead and put those on or in your envelope and move on to the second set. Now, these guys, as you'll notice, all have letters on them. Each letter represents a different fossil, okay? So each letter represents a different fossil. Your job is going to be to put these guys in order, in the only order that makes sense. Now, keep in mind the two rules that you've already talked about. Number one, that the older fossils are on the bottom. That's the law of superposition. And number two, that fossils live through more than one time period. So more than one layer of the earth. So you'll have a letter show up in more than one layer, but they have to be consecutive layers. An organism can't go extinct, disappear, and then show up again. So we're going to start with the one that says TC, okay? That TC, that is the bottom layer of our simulated fossils here. So the one that goes next has to include a T or a C on it, all right? And the only one that has a T or a C on it is CGA. So I'm going to lay these on top of each other, and we'll see that the letter C is a fossil that was in both layers. That's how we know these two go together. Your job is to find the next layer and the next one until you get them all in order. And when you get them all in order, call over the substitute, and he or she will check for you and tell you whether you have the correct answer. And then you can move on to the second activity. So please pause the video here while everyone completes activity 1 and then checks their correct answer. And then we'll get started with activity 2. All right, now it's time for the second activity with the bigger cards that have the actual pictures on them of different fossil organisms. I want you to go ahead and turn them all face up and right side up so you can see them. You'll see there's a variety of different kinds of organisms here. Most of what you're seeing are creatures that had shells. And you should know why that's the case, mainly because not every organism leaves behind a fossil. It must have some kind of body part that doesn't break down very quickly. So you should have a total of 8 of these little squares. And your job is going to be, again, to put them in the right order. Again, the rules are the same as they were with the letters. You need to make sure that organisms don't disappear and then reappear later on. So they have to stay in consecutive layers, and you have to try and figure out what order they should go in. Now, I'm going to give you a hint. The layer that has an M on it is going to be the bottommost layer. So now on top of this, I want you to stack the layers in order so that organisms that are in this layer overlap somewhat with the layer above it, and they go in order. When you're done, again, call over the sub, and he or she will verify that you have the correct answer, and then you can move on to the next activity. Thanks, guys. Have fun. All right, time to pause again while we work on Activity 2 and get our answers for Activity 2 checked. Now that you're done with both activities, we're going to do a little wrap up in your notebook. So go to the bottom of the notes that you took earlier, and we're going to answer some questions. You don't need to write the questions, just the answers, so feel free to pause as necessary. Question number 1. In activity number 1, explain how you knew that the D on the DM card was the same age as the M. And again, you don't need to write the questions, just write the answer in your notebook. Time for question 2. Now we're looking at activity number 2. Which organisms would make good index fossils and why? Don't write the question, just the answer, and feel free to look back at your notes about what makes something a good index fossil. Now question 3. Again, don't write the question, just the answer. In activity number 2, which organisms would be bad index fossils and why would they be bad index fossils? Again, don't be afraid to check your notes about what makes for a good index fossil. Question number 4. In what type of rocks would you find the fossils from today's activities? And why is that the right type of rock? When I ask about types of rocks, I'm talking about the 3 kinds that we reviewed in class on Wednesday. Question number 5. How does today's activity, both activities, how do they relate to the law of superposition? So how are they connected to superposition? Feel free to remind yourself what that means from your notes. And now the last question. What was the most interesting or fun part of today's class for you personally? Make sure you include some details, and you can do one or two parts of class. I'm going to use the information from this to decide how to do future activities. So take it seriously.
Exactly how old was the Earth? The question persisted until 1907, when American chemist Bertram Boltwood discovered a way to make the rocks and minerals of the Earth provide an answer. Scientists already knew that rocks contained naturally occurring radioactive elements, such as uranium. They also knew that each element decayed into other elements according to its own rate or clock, and that rate almost never changed. While studying these rates of decay, Boltwood found that mineral samples of uranium always contained traces of lead. It was an indication he believed that lead was the last element remaining from uranium's slow process of decay. From this observation, Boltwood put it all together. If he measured the amount of lead contained in a uranium sample and calculated it by the known rate at which uranium decays, he could determine the approximate age of the rock. It was a breakthrough discovery. Suddenly, scientists had an extraordinary and accurate new tool for calibrating the geological history of the Earth. It was called radiometric dating.
The great thing about radiometric dating is that it allows us to determine the age of the rocks in the Grand Canyon with quite a bit of precision, so that we can understand the whole history of deposition of these rocks before the canyon was carved. We know that the rocks in the very deep part of the canyon are 1.7 to 1.8 billion years old, and yet they're overlain by a flat surface of sandstone that's only 530 million years. So without geochronology, we would never know that we're missing more than 1 billion years of history across that surface. Now, other places in the world have that history. Here we don't have that history, and that's the important thing to remember. The geologic record is remarkably incomplete.
So a century ago, geochronology, time in the Earth, a century ago, what was it, an accuracy of 10%, 50%?
100 years ago, we didn't even know what we were dating, so uncertainties were much, much larger. They were getting dates of around 2 billion, which, of course, was a huge breakthrough in terms of understanding how old the Earth was, but it was only half of the true age of the Earth. And it really wasn't until the 1950s that people began to date meteorites that we began to realize that the Earth was probably 4.56 billion years.
To appreciate how much time that is, consider this. If we compare the entire history of the Earth to a span of 24 hours, 1 million years would go by in about 30 minutes, which means that the entire epic story of human civilization would be over in less than 1 second. Not even a tick of the clock. So why is this so important?
When we look at the history of evolution is punctuated by incredible extinction events. The Permo-Triassic extinction 251 million years ago killed 90% of everything that lived in the oceans. So the question is, was this sort of a gradual process where we saw increasing amounts of extinction, and then finally the last hurrah, or was it catastrophic? Was life wonderful on the Permian Earth, and then suddenly everything went extinct? The way to answer that question is through high-precision geochronology. And the data that's accumulating right now suggests that it was an extremely rapid event. So as soon as you say a rapid event, the one model we have that works very well is impact of an asteroid. And recently there has been some evidence put forth that suggests there may have been an asteroid at that boundary impacting the Earth. The other aspect of extinctions that's really important, and to some people even more exciting than understanding the extinction itself, is what happens to the ecosystems? How long do they take to recover? When you wipe everything out, it's like resetting the whole evolutionary clock, and then you allow new things to fill the ecosystems that were completely obliterated. It could be that if it weren't for that extinction, we wouldn't have seen the rise of dinosaurs and then mammals. We could live on a very different planet. We wouldn't live here.
You look at this view and you feel like an insignificant speck.
Right.
And the grandeur of it is astonishing, but then when you think about what you can learn from it, then it's a whole nother level of...
It is. And it's like a book. There's lots of information there waiting for us to extract it, information that we haven't even thought about asking the rock record to produce for us. So there's a lot to do.
Well, that's job security for science.
Yes.
The Earth is a complex and dynamic planet. The crust is shifting, the mantle is moving, the atmosphere is constantly in flux. All the species that live on the Earth are changing along with it. Our ancestors did, or we wouldn't be here. The Earth challenges all living things, and so far, life has been up to the challenge.